All right, so at long last, after all these videos, this is like watching a bad movie with no popcorn so far. After all these videos, all this information, at long last, some technique. At long last, something where you need to have an assignment where you can get a final answer and check your answer, and that's going to be correct. All right. So at long last, here we are. This is the technique. I am giving you a statement, and I am claiming this is true. This is my claim. I claim this is a true statement. All right. I claim that for this function, as you get close to 3 on the x-axis, the function value is getting close to 7 on the y-axis. That's what I claim. In this case, so do you see what x and a, I would say a and f of x and L. For this problem, L is equal to 7, f of x is 2x plus 1, and a is equal to 3 for this problem. All right? So what do we need to do? The technique is this. We need to verify this really, because as far as you know, I just picked 7 out of the blue sky. And if we get some other statement, what does that equal to? How do you know that's true? How do we know all this was working out the proper way? What we're going to do is verify this really is the case. This is called a delta-epsilon proof. And anyone who's been through a really good Calc 1 course, if you don't want to have a really good one, you can take mine. But if anybody who's been through a good Calc 1 course has been through the rigors of a delta-epsilon proof. For now, from your side of the camera, what you should be after is a rough, crude, fuzzy, kind of a foggy idea as to what's going on. Be able to follow the nuts and bolts. You'll see this later again this semester. It'll start to make a little more sense. You'll see it again in this Calc 2. It'll make a little more sense. And if you ever get to take an advanced calculus course, then you'll see it again. You think, oh, that's what he was saying back in Calc 1. That makes sense now. And then if you study this some more, you take it in graduate school and you say, oh, that's what we were doing way back in junior level calc. Oh, that's right. And so the more and more you see this, the more and more it becomes part of your mental furniture. And not only are you able to do the work, you begin to understand what it is actually happening. For now, first time through the water, all you need to be able to do is put in the nuts and bolts in the right spot. Don't worry about too much about deep understanding. Hopefully, you're beginning to get a better picture, a better feel for this, and as the semester rolls on, it'll help out some more too. But for now, just be able to get the nuts and bolts of how this works. This is called a delta-epsilon proof. Remember that, I don't know if we know this, in the Greek alphabet, alpha, beta, gamma, delta, epsilon. So delta is where we get D and epsilon is where we get E. And we think of it as the English alphabet. Technically, it's the Latin alphabet. And so D comes before E, delta comes before epsilon. It's a delta-epsilon proof. Remember that delta is on the x-axis, epsilon is always on the y-axis. If you haven't already picked that up because of repetition, at the very least, you pick it up because, if nothing else, the memory device is alphabetical. X comes before Y in the alphabet, and delta comes before epsilon in the literal Greek alphabet, right? Alpha, beta. So delta is before epsilon, X is before Y. This is your very first delta-epsilon proof. I feel sort of, ooh, how happy you must be to see your very first delta-epsilon proof. All right, so here's what we do. This is the technique. There are 3 parts. Remember, there were 3 parts for our work. The definition is that for any epsilon greater than 0, right? If we have 0 less than x minus a less than delta, we got to find the delta. Remember, epsilon's going to be given. We got to hunt and find the delta. And then we have to make sure that that delta works. We have to make sure that that delta causes absolute f of x minus L to be less than epsilon. So there are 3 parts. Anytime, if you're doing work for me, anytime you're doing any delta epsilon proof for me, there are 3 parts, count them, 3 parts. If you do not have all 3 of these pieces there, then as far as I'm concerned, you don't have all the work done, it's not complete, you're not getting full credit out of me. Way back in when I took Calculus 1 with Sam Lessig, he did not give us full credit if we don't do all 3 steps, and there's no way in God's green earth I'm giving you full credit unless you do all 3 of these pieces, every one of them. Number 1. let epsilon be greater than 0. So that's always step 1 in a delta epsilon proof. I don't care what else you're doing. Step 1 in a delta epsilon proof is let epsilon be greater than 0. In math majors, that's like when you come out of graduate school as a math major, the very first thing on your lips is let epsilon be greater than 0. You go to the bar, what do you like to order? Let epsilon be greater than 0. Let epsilon be greater than 0 is like the mantra of all math instructors. You go to any math instructor and say, let epsilon, they'll say, let epsilon be greater than 0. This is like the one true faith for us. Let epsilon be greater than 0. And number 2, we got to search for delta. Every time, number 1, let epsilon be greater. So you will write 1, circle around it, let epsilon be greater than 0. Then you will write 2, circle around it, search for delta. Style matters. Style matters. If you do the style correctly, that will help you in the long run to get the actual details correctly. So, number 1, let epsilon be greater than 0. Number 2, search for delta. Now, the way you search for something is you start where you want to finish and back solve for it. You've done this dozens. Anytime, as soon as I say the word back solve, that should set something in your mind. I want you to recall something. Recall your glory days way back in basic algebra when you wanted to solve something like this. Remember solving, I have a little equation here. Here's my little example. X minus 2, and I had, what did I have? Something simple. Plus 5 is equal to 1. Remember solving equations like this, right? You solve this dozens of times, right? No big deal. What do? Well, you know what? Subtract 5, and you get square root of x minus 2 is equal to, what is that, negative 4. You square both sides, you get rid of the radical. You get x minus 2 is equal to, that, 16. And then, add the 2 across, you get x is equal to 18. And then you put a box around it like you're proud of it. Do you see it? Do you see what's gone wrong here? Do you see the mistake? Well, there is no mistake. There is no mistake, but that's not correct. How do you know that's not correct? What are you supposed to be able to do with your solution when you finish with it? Yes, you're supposed to be able to take x equal 18, stick that up into here, and this stinking better work. Well, what happens? What happens if I take 18 and put it in for x? If I take 18 minus 2, take the square root of that and add 5. What the heck? That stinking better give me 1. Well, let's see, 18 minus 2, that's 16 square root plus 5, which is 4 plus 5, which is 9. And I don't know all mathematics in the world. I know 9 is not the same thing as 1. I know that. What has gone foul here? Well, there's something has gone foul, but the point is this. You search for the solution, but some equations are more subtle than others. It turns out the reason that you need to check this result is because the domain of the function is not all the real numbers. That's not really a big deal for us right now. But the point is this. When you get your candidate, if things are subtle, now if all you're doing is solving x minus 4 is equal to 8, yeah, you can solve that and you got it and you're done. That's all there is to it. But if things get more subtle, when you get your candidate, you stinking better check to make sure it works. In this case, what that means is this doesn't work, there's no solution. So that's what's going to happen here. The first piece is we need to search for delta and find delta, and then step 3, you must verify. You must verify that delta actually does what we say it does. Because we're staying in the shallow end of the pool. We're not staying in the shallow end of the pool. We're staying in the shallow end of the baby pool. Because the problems we're going to consider are so straightforward, it doesn't look like you're doing much here. But we'll see what happens here later on. So, this is how the delta epsilon proof. So I'm going to prove this statement to be true. I'm going to prove this is true. This is what you need to be able to do. This is a technique you need to be able to apply. Prove or verify this actually is a true statement. Okay? So number 1. Okay, verify this. I'm going to use a delta epsilon proof. All right? Number 1, let epsilon be greater than 0. If you don't include that, it's not correct. I don't care what you do. I don't care if you find a cure for cancer. You're not getting full credit out of me unless step 1 is let epsilon be greater than 0. Number 2, search for delta. Here's what you do. You start at the finish. Remember, recall the thing. This is the definition. For any epsilon greater than 0, there is a delta such that okay. That's the requirement. Remember, this is what it means. This statement, limit statement, means this. For any epsilon, there is a delta. Remember, the 0 less than this means they're not equal to A. Such that if this is true, that will cause this to be true. Anytime this is true, this means this is true. Epsilon's given. We got to hunt and find the delta. We got to find the delta, and then we got to show that using delta here will cause this to happen. Here's the technique. The search for delta is this. You start with how you want to end. You start at the end. You start where you want it to end. You always start with this. You always start with this. You don't start with substituting these in first. You start with this statement. Every stinking delta epsilon proof you do for me, it's going to have that written on it. It's going to have that written on it. It's going to have that written on it. Every stinking one of them. This technique matters. As this becomes more complicated, if you don't use correct technique, you will begin to fall off the beam. Technique matters. So write this piece. This is where you want to finish with. Now, translate that in terms of the specifics. So this goes in for f of x. Use the parenthesis. Minus L. What's L for my problem? L is 7. Is less than epsilon. And I'm going to use this space right here. Right? Now, the technique is this. In this absolute value, you use your vast repertoire of algebra skill to create absolute x minus a here. Change this algebraically so it becomes x minus a. In this case, x minus a is x minus 3. So you need to create x minus 3 in here somehow. The way you do that is by just straightforward algebra simplify. Absolute, this is 2x, what is that, minus 6, is that right? All right. And we want to create x minus 3. Do you see how you can create x minus 3 in here? Do you see it? Now look, if you factor out the 2, you've created x minus 3. That's what we're after. How do you know you want to create x minus 3? Because you know you want to create x minus a, and in this case, a is 3. So factor out the 2. And you can apply the property of absolute value. The absolute value, there's a property of absolute value. The absolute value of AB is equal to the absolute value of A times the absolute value of B. It's not very hard to verify that. Just go through the various scenarios. It's always correct. The absolute value of the product is the product of the absolute value. So we can write this as, this is A, this is B. And you see it? Bing! I just created x minus A. There's my x minus A. Solve for that. So divide both sides of this equation by absolute value of 2. If you want to just write this as 2, that's fine. But divide both sides of that equation by absolute value of 2, and you generate x minus 3 absolute is less than. Divide both sides by epsilon over absolute 2. Now, how do I know? When do you change the direction of the inequality? You change the direction of the inequality if the number you divided by is negative. Is it clear? The number I divided by is never going to be negative because it's always going to be absolute value of something. Even if, we'll do this in a later example, even if this had been negative 2, absolute value makes it positive, which means this stays as less than. So this absolute value, just leave it on. I know you could take it off, just leave it on. You'll see why later on. If you get used to just leaving the absolute value on, it's going to hold you in good stead. As soon as you create x minus a, what are we doing here? We are searching for delta. And here's the deal. We choose delta equal to whatever's on the right-hand side. Whatever is on the right-hand side, that's your delta. As soon as you create x minus a, whatever's on the right-hand side, that's your delta. Epsilon over absolute value of 2. So, let epsilon be greater than 0. Search for delta. Start with the end and work back. What you're doing is you're back solving. Very similar to what I did with that absolute with that square root equation a while ago. Start with where you want to finish, back solve, and you've chosen your delta. So we did that. What's left is we have to verify delta. So this is step 3. And I've just erased that, but because I'm running out of space. So step 3 is verify delta. And now you start at the very beginning. I don't care what else happens. If you're doing step 3 to verify, step 3 verify always, 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 always. Step 3 verify delta always starts with this generic statement. You do not, you do not start by putting the 3 in at the very start. No, not if you want full credit out of me. You're not getting full credit because you left a piece out. You start with the generic statement, and you need to end with the generic statement. You'll see what I mean here in a minute. That piece. Now you begin to substitute in all these little statements. In our problem, what is A? A is, where's our problem? A is 3. What was delta in our problem? We chose delta somewhere. Delta is epsilon over absolute 2. You're saying, but Regis, you left this piece off. Okay, I stated it once. What does this mean? This means x is not equal to a. So, x is not equal to a. Once you've said it, you don't need to keep repeating yourself. X is not equal to a, x is not equal to a, x is not equal to a, x is not equal to a. You say it once, you don't need to repeat it. So stay it once, and then you don't need it for the rest of the way down. State it once. There, it's official. X is not equal to a, and x is never going to equal a from here on out. So you don't need that every time. Just once at the very beginning, and then you may omit it. You've already stated x is not equal to a. Now, recreate what we had before. Solve for epsilon. So this is the same thing as saying absolute 2, absolute x minus 3 is less than epsilon. That's the same thing as saying, we're going to use this in reverse now. Absolute a times absolute b is absolute ab. Absolute 2 times absolute thing is absolute 2 times thing. And I'm going to move up here now. So I'm continuing my work here at the top of the column. Distribute. And you're trying to recreate, what you're trying to recreate is absolute f of x minus L. That's what you're trying to recreate. It's almost there. Look, it's almost there. You see it? It's almost there. The next piece, the next technique, this is all this is. This is technique. The next piece is, we don't want x minus 6, we want x plus 1. So fix it. Here's how you do that. Pick any number on God's green earth. 29. 29. This, you don't write this, but just follow me. If I do plus 29 and minus 29, this, I have not changed anything, and this is still equal. This is equal to that. If you add 29 and subtract 29, this is still equal. If you don't like 29, you can add and subtract any number on God's green earth. I want to add and subtract 40. There. You can add and subtract any number you want. Well, what number do you want? 1, that's what you want. So you force the number you do want, and then you account for it afterward. Add 1 because that's what we want, subtract 1 because that's just the accounting. And so what do we have now? This piece is the 2x plus 1. What is that piece? Well, what a stunning coincidence. And now the last little bit, what is 2x plus 1? That's f of x. What is 7? 7 is L, is less than epsilon. So you start with the delta statement, and you argue, and you create the epsilon statement. You always start with the generic statement, work, and you end with the generic statement. Okay? So I'll go through several examples of this. It's not quite so problematic if you don't need to explain it while you're doing it. And I think after you've combed through this 2 or 3 times, you'll be able to handle anything I'm going to throw at you. So what we'll do now is we'll let this sit, and I'm going to come back in the next video and do several examples of specific functions, specific values of A, specific values for L, and get you used to doing this. It'll become part of your mental furniture.